But we're going to talk about echelon form, reduced echelon form. These are topics in linear algebra. So this is what we're going to do. Now, a system of linear equations can have one of the following solutions. It can be no solution, exactly one solution, or infinitely many solutions. And here's an example of what a system of linear equations would look like. And we're going to learn how to solve it here in this video. Now, with matrix notation, we have to take our example equation and put it into what's called an augmented matrix. Do it a little bit better. But we have a coefficient matrix. We have a 2, a 3, and a 7, a 3, a 4, and a 5, then a 1, a 2, and a 3. And that's our coefficient matrix. And then what I want to call a solution matrix is going to be 24, 9, and 13. So to get it to the form that we need it in to solve for the system of linear equations, we're going to put it into this form. We have a 2, a 3, and a 7, a 3, a 4, and a 5, a 1, 2, and a 3. And in this last column, we're going to put 24, 9, and 13. So that is our augmented matrix. We need one more tool or one more piece to be able to solve a system of linear equations, put it in an augmented matrix, and then get it into reduced echelon and echelon form, which I'll explain in a second. So the first one that we'd like to look at, and these are elementary row operations. These are only row operations we can use when solving for the augmented matrix. The first one is the replacement. And what the replacement is that you multiply one row by a constant, and then you add it to another row, and then this particular sum here becomes that row. So if, for example, I could take 3 times R1 and then add it to RJ, and then this sum becomes RJ. The second row operation that we have is the interchange. And this just means that we can swap any row with another one. And that's all there really is to it. And then the scaling row operation is we can multiply any row by a scalar. So we could have negative 1/2 R1, and then that would be our new R1. So there's many different ways to use these row operations when we're trying to solve an augmented matrix for a system of linear equations. I have one more note about the row operations. Anytime you use the replacement or the scaling in the constant here can never equal 0. So now we're going to take a look at echelon form and reduced echelon form, the actual topic of the video. And here we have 5 conditions that we're going to look at. The first 3 conditions conform to echelon form, and the last 2 conditions build on the first 3 and will ultimately give us reduced echelon form. So the first condition for echelon form is that all non-zero rows are above any rows of all zeros. The second condition is each leading entry of a row is in a column to the right of the leading entry, and all entries in a column below a leading entry are zeros. So those are the conditions that a matrix must meet for echelon form. We'll explain all of this in just a second so you can see it. And then the conditions for reduced echelon form, in addition to the first 3 for echelon form, the leading entry in each non-zero row must be a 1, and each leading one is the only non-zero entry in its column. And like I said, we will take a closer look at this in just a second. So the system I'll be using is going to be x1 plus x2 plus x3 equals 1, 2x2 plus 2x3 equals 6, and 3x3 equals 13. So the first step is going to put it into the augmented matrix form. 1, 0, 0, 1, 2, 0, and then 1, 2, 3, and 1, 6, and 13. So this is in echelon form. Now, I don't know if you can see that just yet. It's an echelon form. And we're going to use our row operations to get it to reduce echelon form and find the solution. So let's continue. So my first row operation is I'm going to do negative 1/2 times R2 plus R1, and I'm put that back into R1. So the matrix will become 1, 0, 0, 0, 2, 0. Let's clean that up a bit. And 0, 2, 3, and negative 2, 6, and 13. And I'm going to keep going. And I'm going to divide R2 by 2 and go that into R2. And let's add some more space here. And we're going to get the next matrix is going to be 1, 0, 0, 0, 1, 0, 0, 1, 3, negative 2, 3, and 13. So that's our next step. Then the step after that, we're going to do 2 operations in one to save time. So we're going to R3 divided by 3 into R3, and then we're also going to go with negative 1/3 R3 plus R2 into R2, and so that matrix is going to become 1, 0, 0, 0, 1, 0, 0, 0, 1, negative 2, negative 4 over 3, and 13 over 3. And so using our conditions above, we see that this is an echelon form. We have a leading entry of 1, 1, and 1, and there are no other non-zero constants in the columns where we have our leading entries, and all our conditions have been met. So let me just add a bit more space here so we can get the final solution. So our solution for that system of linear equations is going to be that x1, let's clean that up, that doesn't look too good, x1 equals negative 2, x2 equals negative 4 over 3, and x3 is equal to 13 over 3. And that is our solution for the system of linear equations